Robin, can you still hear us?
Yep, still good.
Okay, great. I think we're good to go now. So we're going to give you a quick intro.
Yes.
Okay, excellent.
So I think here will be able to learn is Robin Walters. Robin Walters is an assistant professor of computer science at Northeastern University, the director of the Geometric Learning Lab. His research is on synthetic learning. The research includes functional theory of learning through the lens of symmetry, to development of new equivariant models for applications of equivariant neural networks, to diverse applications in science, engineering, including, of course, robotics. We're very excited to hear about your work, Robin.
Robin, did we lose your slides?
Do you not see them? I still see.
It might be my fault. Hold on, I'll switch to shared content. There we go.
Yes.
Okay, we should be good now. Take it away.
Great. Okay, thank you for the introduction and thank you for the invitation. This is a really great workshop. I'm a big believer in this field. I definitely wanted to be there in person, but I had some unfortunate passport issues, so I'm here virtually. So I work on problems applying deep learning to dynamics and control problems. And these domains are a little bit different than language modeling. I see three big challenges in this area. One is poor generalization. Another is the limited amount of data in these kind of domains. And the last is a lack of physical grounding or physical fidelity. And these are not problems that we can, just fix by building larger models and adding more data. We need some more sophisticated solution. So the method that I pursue and that I think is generally the philosophy of people at this workshop is to incorporate symmetry into deep learning. So when you build symmetry into deep learning methods, you get automatic generalization across the symmetry group. You get more data because this sort of results in automatic data augmentation across the symmetries. And lastly, you're sort of building in some sort of physics into the model because symmetry goes hand in hand with conservation laws. So it's part of the title of the workshop, but I'll say that the way we identify symmetry, or I identify symmetry in models, is I look at my ground truth task function, mapping some input to some output space. And I say that this function is equivariant if when I transform the input in some way, the output transforms in a corresponding way. So here I'm showing a segmentation task where if I segment this image, if I were to first rotate and then segment the image, that's the same thing as if I were to first segment and then rotate. So that's an rotational equivariance of the segmentation task. So that's just about an observation about the ground truth function, right? The next question is, how do you incorporate that symmetry into a neural network model? So there are a couple different strategies. Maybe the most traditional one is to canonicalize your data in some way. Another method that is extremely effective to this day is data augmentation. So just adding transformed samples to your training data. But the method that I prefer is equivariant neural networks. So these are model classes in which the layers are constrained to follow the symmetries of the problem. So if I have two layers, in this case, R2 and R4 are the spaces, and I have some linear mapping between them, right? Normally, there would be 8 trainable weights in a 4x2 matrix, but when I impose a symmetry constraint on this matrix, I end up with some sort of weight sharing or weight tying pattern. And this matrix will actually always reflect the symmetry of the problem. It will always be equivariant with respect to those transformations. So I can impose weight sharing on a neural network and I get an equivariant model class. And this is sort of the picture that I like to draw. We have the space of all of some large neural network model class. And here what we're doing is we're applying a constraint to the entire model class so that we end up with a smaller space of equivariant model classes. And that means that at initialization, we already have the correct symmetry, and that holds throughout training. It's now a constrained optimization problem, if you like. And there's the true function that is equivariant. And so we're training within the right model class. Okay, so now I'm going to talk about applications of equivariant neural networks in robotic manipulation. So we have this picture that's sort of similar to the segmentation picture I showed earlier. So we just have to look at the set task we're trying to solve and ask, what is the symmetry? So here we're trying to move this yellow block. Our state represents the position of the yellow block, and we perform an action, which is to push the block. So I can kind of animate this, right? So we're pushing the block. And here we're demonstrating that this task actually has these transition dynamics have this rotational equivariance, which is if I were to rotate the entire scene 90 degrees and then also rotate the push, then I end up with the rotated position of the block, right? And that, of course, is the same sort of thing that almost all equivariance derives from, which is that my coordinate frame was in some sense arbitrary. So as long as I'm transforming everything consistently that's described with respect to that coordinate frame, I have some symmetry or equivariance in the problem. Okay, so there's some theoretical work that sort of says if you recognize that you're working in an MDP with transition dynamics and reward that have some symmetry, then it's true that the optimal policy and the optimal Q function for that MDP are also symmetric. In particular, right, notice this reflects exactly what we just saw in the last slide, that in the optimal policy, if I transform the state, then the action needs to be correspondingly transformed, which we call equivariant. And for the Q function, which is just giving the like expected reward under the optimal policy, we have that it's invariant, meaning if I transform both the state and action, I should have the same reward. Okay. All right, so how do we leverage this information? So if we're learning some policy and we're doing some deep, if we're parameterizing that policy with some deep neural network, then since we just realized that the problem is symmetric, and that means that the policy is going to be equivariant, then we could learn that policy using an equivariant neural network. And now we have a leg up on learning that policy because we've already constrained it to have the property that we desire. Okay, so how did we apply this? So we took this realization and we designed SO2, or rotationally equivariant reinforcement learning algorithms. So here I'm showing an equivariant soft actor critic problem that we're going to apply to closed loop manipulation problems, right? And on the left, I'm just showing the schematic that shows the actor, which parameterizes the policy, is going to be equivariant. If the state rotates, then the action push direction also rotates that it outputs. And then on the right, we have the critic function, which takes in both the action and the state. And if both of these rotate together, then I would get exactly the same Q value. And these constraints are going to be built into the network. And then we train them by reinforcement learning. Okay, and what do we see? So on the left, we have the conventional SAC algorithm with no symmetry constraints. And on the right, we have the one that has the symmetry constraints. And what we're looking for, this is trained in simulation, so this doesn't take too long. But you can imagine if you're training on a real robot, this could take quite some time. And what we're seeing is that the equivariant one learns a lot faster. In particular, once it has learned to open that drawer once, when we reinitialize the scene to a new initial condition, it generalizes that success to the new condition because it is a rotated or translated version of the old one. Once it has learned to solve the problem once, it recognizes that transformed initial conditions relate to the old initial conditions, and it can apply the same policy. The old SAC basically sees new data every time we reinitialize this, and it has to relearn the same task over and over for each sort of position and rotation of the drawer. So we get much sped up learning process, right? Here we're showing a couple more tasks. This is comparing our equivariant SAC to like a baseline CNN, which is very similar with no equivariance constraints, as well as RAD and DRQ and FIRM. So these are strong baselines that actually also leverage symmetry, but they do it through various systems of data augmentation. So that's a question I often get is how does putting equivariance into the layers of the network compare to just using data augmentation? And the answer varies depending on which paper you're reading and in which domain you look. But I think in this case, the answer is pretty clear that within the time frame I'm showing here, which is 20,000 iterations, the data augmentation methods have not even begun to learn the task. They will probably eventually, but it will take much longer. So this is the dream for us, which is to avoid sort of sim to real entirely. And these algorithms are so data efficient that we can train them very fast entirely on real robots. So here are various grasping tasks, including a clutter grasping task. So here's a demo. So this video lasts an hour and a half, but it's been sped up. And this is training from scratch on a clutter grasping task using the equivariant grasping algorithm I showed before, and it sort of like starts moving around a little bit, but eventually it sort of gets it. And now what's going on? Well, the model has a local symmetry to it. So once it has sort of learned to pick up each of these objects in some orientation, it can now generalize to the other orientations. And so this can all be trained from scratch. And I believe the previous best for a task like this for on-robot learning was on the order of hundreds of hours. And we've got it down to an hour and a half. And my students actually set up this demo last year at a conference hall, and it's great because within the course of a poster session, you can watch this train from scratch. Okay, but this sort of like high-level idea, which is basically that the policy is equivariant and it could be constrained with an equivariant neural network to make it be learned faster, is not specific to reinforcement learning. We can use it for imitation learning too. So here we're directly training the policy for some manipulation task using expert demonstrations with supervised learning. And we just do the same thing. So in this case, we constrain the policy to be an equivariant neural network. And we know that that's true based on the theory, that's true of the optimal policy based on the theory that we saw before. And so now we can see what happens. So here I'm sort of demoing a different consequence, which is that sample efficiency is great, but equivariance also results in greater accuracy. And I think we see this a lot in imitation learning. When you're learning from very few demonstrations, those demonstrations can cover a pretty small part of the state space. And the resulting policy can kind of be brittle with respect to different initializations. And so by applying equivariance, essentially what it does is it takes the expert demonstrations and it augments them across the symmetry group so that you're actually, from those few demonstrations, exploring a lot more of the state action space. And that makes it less brittle and able to complete the task better from different initial positions. Okay, so here's sort of our most recent work. So this is the equivariant diffusion policy. There are a couple of these now. Ours works from a couple, so ours is based on high dimensional inputs, so it can work on RGB cameras, RGBD cameras, it can work on point clouds, it can work on voxels. But the idea is pretty simple. So what diffusion does is it starts with a noisy trajectory, and through a process of denoising, the model eventually decides what trajectory it should take. And what diffusion is particularly good at is representing multimodal action distributions. So here, it has to move the arm around this blue block, which is an obstacle to reach the screen. And, I think this is the third or fourth diagram I've shown like this in this talk, but you can see that if I were to rotate the scene, then sort of the entire diffusion process can rotate. And so that means we have equivariance. And in this case, you can apply an equivariant constraint to the denoising network. In other words, the sort of vectors that move you from the initial trajectories to the optimal trajectories just rotate with the scene. And I think that equivariance plus multimodality is a really big win, because essentially what in a non-equivariant policy may result, especially in an imitation learning setting, as just sort of learning one mode, will automatically get copied by the equivariant network to see all of the modes that are transformed versions of that mode. Like in this case, if there's some I'm not showing it here, but if there was some reflectional symmetry where you could go around either side of this object, the equivariant network would automatically learn that from a demonstration on only one side. And to some lesser extent, it still sort of gets a leg up on doing that, even if the problem is not exactly equivariant. So here's the big payoff video. So this is sort of this combines the sample efficiency and robustness that I showed earlier and allows us to very robustly learn very long horizon tasks. So here's this sort of bagel baking task. I always make fun of Deanne because I don't know who doesn't put cut the bagel first before putting it in the toaster oven, but that's That's the way that it works. So this is a collaboration with Boston Dynamics AI Institute, by the way. So these videos were recovered over there. And here's the generalization to different initial conditions that are outside of the demonstrations. I should mention this is 58 demonstrations that this is trained on. I think there were 60 originally, but there is a problem with 2 of them, so 58. And then, you know, just to, maybe I just wanted to skip a little ahead in the video to show. I think we do. Is it what? Is the video okay? I know it's kind of, yeah. So there's like some trash sweeping, clean up the workspace after your experiment. And letter alignment. So you can guess where the paper was submitted. All right. Okay. Now the title of my talk is about pushing the limits of equivariant neural networks. So, you know, my natural inclination when I see a great method as an academic, as opposed to someone in industry, is what are the limits? How does it fail, right? And I think the failure cases for equivariant networks are pretty clear if you think about them, which is that we're assuming an environment with perfect symmetry. We're assuming we know that symmetry. And we're also assuming that we know, this one's maybe a little more subtle, but we know how to apply that symmetry to the problem. So if you actually want to go build an equivariant neural network, you need to sort of have the Python function available that would transform your input sample, right? So that doesn't always happen in real world. The real world's noisy and we're learning from real world data. So we can have various symmetry breaking, we can have unknown boundary conditions, we can have noise that isn't correlated with the underground symmetry in the physical state. And in robotics, I think just like a really simple example is like this duck rotating where we're coming at it from a side view. And we don't have that perfect top down, which was the symmetry that I was showing earlier. So what do you do in these cases? So I'm going to briefly talk about three options. So the first option, I think, is a bit funny, but it basically says, what if you just apply an equivariant neural network, even though you have a mismatch? So I'm showing this instance where basically we're looking at the duck from a side view. The symmetry I want is the rotation of the duck in the world, right? But that's kind of if I had a top-down view, then that's exactly what I have in my image capture. But I don't have that. I have this side view. So what the neural network is actually easily able to be equivariant with respect to is rotations of the image, not rotations of the duck. There's a mismatch between the kind of symmetry I can put in the network and the kind of symmetry in the problem. So we call that, we termed that extrinsic equivariance. Extrinsic meaning that there's some distance from the symmetry group action in the model and the symmetry group in the data. And what we showed in this paper, that I think this was at iClear, is that actually you don't get as good performance, you know, as if the symmetry is matched. But surprisingly, in a wide variety of situations, you actually do get a benefit from applying the equivariant model to just symmetry transformations. You basically pretend it's a top-down image, even though it isn't. And I don't have the plot here, but as you would expect, as you increase the angle from top down to side view, performance degrades, right? And what that means, but very importantly, so the blue line is our method here. You should still do it. Like the equivariant performance from a slight side view is much better than the performance without equivariance at all. So it's not necessarily the case that just because the assumptions are violated means you have to throw equivariance out. Okay, another method is to learn a symmetric representation. So if I don't know how to transform the system state because it's not in a form that I know the group action on, then I can try to learn that thing. That's kind of the knee-jerk reaction for deep learning people. So here what I'm showing is this SCN. So this is the idea here is that I have some high input where I can't transform it easily. In this case, I'm showing a 2D image of a car, but the rotations are in 3D. Transforming this car to rotate 45 degrees from this kind of observation is novel view synthesis. I can't simply write a Python function, so I can't build an equivariant neural network. But I can learn to map this high-dimensional observation to a vector that I can transform, and then I can have a downstream equivariant neural network operate on it. So that's the idea. And here's the results. So what you get in this case is you train from side view, you train from 2D images of 3D things, and you can learn a representation that actually that the symmetry group can act on. Here, what we're doing is 2D images, and we're learning a 3x3 matrix, which is supposed to be the pose. And the secret is sort of that there's no secret. We just take that 3x3 matrix that is supposed to be the pose, we feed it into a downstream SO3 equivariant network. And it will only work if the downstream network, if the 3x3 matrix actually learns to be the pose. So here we're essentially learning the pose of the teapot with no explicit labels of the pose, simply because that's what the equivariance demands of the problem. And the visualization here is that we're taking the transformation and that the network learns, and we're simply applying and re-rendering the teapot so you can see a visualization of what the latent space representation of the pose is. And you can see that they rotate together. Now in latent space, there's no way it can know what the what the zero or initial identity pose is. And so that's why there's an offset, but that's irrelevant for this problem. Okay, and the last option before I wrap up my talk, which I think is probably the most intuitive option, but I'm going to do it last, which is to relax the equivariance constraints of the model. So if the true function is not exactly equivariant, then can we build a model class that doesn't have such strong constraints, but still benefits from some inductive bias of symmetry? And I think the picture kind of shows what happens pretty well. Basically, we introduce some weights to the equivariant convolution that formally mathematically break the constraint. And then during training, the model can acquire gradients that push those weights off of the exactly symmetric solution. We initialize it to be equivariant, and you end up with sort of an approximately equivariant kernel. And you can see that we're sort of, we're close to the equivariant setting, but we've got some adaptability. Maybe gravity is in the vertical direction. And so far, we've applied this method to dynamics prediction, which is one of the things I've worked on. But I'll tease that we have a paper coming out soon where we also apply relaxed equivariance in the case of reinforcement learning as well. All right, so here are my collaborators. Thank you very much. Are there any questions?
Thanks so much for the great talk, Robin. We've got time for maybe one or two questions.
Thank you. Hi, thank you for the talk. I was wondering about the equivariance. I'm assuming that the demonstration you showed trained in the task space with 10-year control of the task space. But if you were to apply those soft constraints that you were talking about at the end, could you perform these tasks or perform learning for configuration space actions? Or have you tried that for doing that?
Sorry, I can't hear that well. What was the last part?
If you were to perform the soft constraints, or if you were to soft to constrain the neurons, could you perform task actions in the configuration space, plans in the configuration space?
Could you hear that one, Robin?
Sorry, no, I can't hear very well. Do you mind?
The question was, can you hear now?
Yeah, I can hear you very well.
The question was, if you were to apply the soft equivariance framework, could you consider actions in the configuration space? Was that the question? Yeah.
Oh, yeah, okay, great question. That's a great question. I think we have one paper where we touch on that a tiny bit with Lin Feng here. And you absolutely could. All you have to do is define the, kind of like a lot of what the thing you have to do in this problem is figure out, how your symmetry sort of like instantiates over different spaces. So you just have to figure out how the symmetry is described in configuration space. Now, depending on like exactly what that looks like for a given robot and what abstractions you might have added, that may be less or more complicated. Like, for example, like a rotation can actually be, pretty complicated in joint space, right? So that's the subtlety.
Thanks so much, Robin. I think we have to end on questions there now. We can save other questions for the panel discussion this afternoon. So now we're going to head downstairs to the, not downstairs, upstairs, and then across, then downstairs, then into room 4, as you can probably figure out on the way here, to the poster session, which is in the main workshop room on board 7.1 through 7.8. So we'll go over there with the poster session, and then we'll be back here for 2 more great keynotes from Elise and Nicole and then Rock a little later today. Thanks, guys.
If you don't mind me just quickly breaking in, let me just quickly say, Deanne Wang and John Park, with whom these works are on the job market. So if you like what you see.
You didn't hear that. Robin said Deanne Wang and Jeremy Park are on the job market. Who were involved.